Hi everyone, I'm Professor Burgesser, and in this video we're going to be looking at how we combine our different techniques of energy, kinematics, and force diagrams, Newton's forces, applying Newton's force laws. I'm going to take that back from the start.
Whenever you're ready.
Okay. Hi everyone, I'm Professor Burgesser, and in this video we're going to be looking at how we combine our different techniques of using energy, forces, and kinematics to solve different kinds of problems. Now we've seen that we can use these different approaches separately to solve some problems, but other kinds of problems may involve using all three of these approaches to look at different stages or different quantities that we have to solve for a particular problem or question that we're asking. So let's look at an example, and this is an example in the case where we are at an amusement park and perhaps we are the designers of an amusement park ride, for example a roller coaster, and we want to design this roller coaster in such a way that the roller coaster car can make it around a loop-de-loop and without crashing down and actually making it all the way around and passing through. Of course there's obvious safety and insurance issues why this is an important question. Now so this situation, we have some kind of descent that this car is going to go down. It goes around a nice circular loop-de-loop and hopefully progresses out along the other edge. And the question is, how high do we want to start this roller coaster in order to make it around this loop-de-loop? So now let's look at what are the things that we know about this problem and what we're trying to solve. So the things that we know when we look at the text, we can see that we're told that the roller coaster car starts from rest. And so that tells us that our initial speed is equal to 0 meters per second. And since we are possibly looking at an energy perspective, it's important to look at what the kinetic energy is. And that initial kinetic energy is going to be 0 joules because it has 0 speed. All right, now what else do we know? Well, we're told that we can neglect friction and drag forces, which are both dissipative forces. And so there are no dissipative forces acting. And that means that we can apply, potentially, energy conservation as a way of solving this problem. Now we're asked to find the point where this is going to complete the loop-de-loop. All right, that's right here. We want to figure out when it completes a full loop-de-loop. And we can think a little bit about what that means to actually complete the motion. And from the perspective of this roller coaster, of course, that means that it makes it all the way around this loop-de-loop while staying in contact with the track. So not completing might be only making it up a little bit of ways and rolling back down. It might be coming up to some point and then not quite having enough speed to go around and then kind of falling off the loop-de-loop, which would be bad. And so the real problem is asking, can we go all the way around this little circle while maintaining contact with the track itself? And if you remember, anytime there's a contact between two surfaces, there's going to be contact forces, the normal force and the friction force. Now we've already neglected the friction force for this problem for the time being, so that means that in order for this to stay in contact with the track, that means it's going to have a normal force, or a magnitude of the normal force, that's always greater than 0 around the entire track. So this sets the parameter, or the constraint, for the problem that we're trying to solve. Now what are we trying to find? Well, that says very clearly that we're trying to find the initial height that the roller coaster starts at, so we'll call that h0. And that initial height is just wherever this starts up here. And of course, since we are talking about energies in terms of speeds, that immediately sort of suggests that we're going to be probably applying an approach of potential energy, so that the initial potential energy is mg times our h naught. Now we can also make some predictions about this motion, and in order for this thing to move all the way around the loop-de-loop, obviously it has to have some speed as it's going around that whole loop-de-loop. And so you can imagine that maybe a prediction for this initial height is that it better end up at the same height as it makes around the loop-de-loop. And so that suggests that h naught is probably greater than 2 times the radius of the loop. That's what we would predict. All right. So now we've got a starting point to start thinking about this problem and how we can approach it. And we have many different ways of approaching it, as we'll examine in this problem. But the first thing is, if you're ever in doubt how to really start, you can start from the perspective of a force diagram. We can look at, for example, where the cart is at a particular angle. So I'm going to measure my angles here and set up a coordinate system where I'm measuring my angles with respect to the bottom part where we're actually starting our loop-to-loop. And we can look at what happens at the forces on the cart as it reaches one particular angle along this circle. So let's draw a quick force diagram for that particular point. All right, so I'm just going to represent my roller coaster car by just a square here. And we know that there are forces acting on it due to weight, right, m times g, because we are in a gravitational field. And as long as we're assuming that this is in contact with the track, we have to have our contact forces. And of course, one of the important ones is the normal force, which is going to act perpendicular to the track itself. Right? And again, this is happening at a certain angle, which we can sketch in here, theta, with respect to the center of the circle. Now, this motion is circular, and anytime we have any kind of circular motion, the coordinate system that's sort of best for use for this is a polar coordinate system. So that's the polar system we want to actually use. So polar coordinates. Fortunately, the normal force is always going to point in the radial direction, or I should say inward in the radial direction, because it's always perpendicular to the circle. But this gravity vector is always pointing straight down, and so we have to break that vector up into its components along the polar coordinate system that we're using. And so that means just looking at the portion of the weight vector that's perpendicular to the normal force and parallel to the normal force. And that's going to be mg times sine or cosine. And again, here's a good place to start thinking about how you would guess those angles. If we're at this initial point, then mg is pointing exactly in the opposite direction of the normal force, and that's going to be purely in a radial direction. And that means that whatever angle term we have, if at angle equals 0, it better give us a 1. And if you remember your angles, that means that's going to be cosine theta. So we can just write that down. And that means the other one is mg sine theta, and this takes the place of our mg vector. And now we've got all of our forces along the coordinate axes that we're using for this problem. So now it just comes back to our regular application of Newton's laws, where the sum of the forces along a particular axis, in this case we'll look at the radial vector axis, is equal to the mass times the acceleration along that radial direction. Now, if we write down the forces here, if we look at, we've got mg cosine theta acting outward. We've got the normal force acting inwards. And this is equal to the radial acceleration. And remember, when we're talking about a circular motion problem, this is going to our kinematics, that radial motion is going to be equal to the centripetal acceleration. And that centripetal acceleration has to be pointed inward. It's pointing in the direction to keep the object going around the circle. It's accelerating, it's changing its velocity in a way to keep it around in its circle. So this gives us minus mass times the centripetal acceleration, or minus mass times, and let's use our expression for speed squared divided by the radius of the circle. All right? Now, looking at this a little more closely, we have a term that's mv squared, which is just like our kinetic energy term, 1/2 mv squared. And so, in fact, we can replace this with 2 times 1/2 mv squared divided by r, and there's a minus sign out in front there. And that means that this term is just equal to our kinetic energy at the point that it is along its circle. So we can rewrite this then as the normal force, because that's something that we're interested in, is equal to minus 2 times the kinetic energy divided by the radius. And then, so let me actually take a step back here, because in fact what I want to do is move the normal force over to this side of the equation and this over to that side. So that's going to be plus 2ke over r plus mg cosine theta. All right? So we've written our normal force in terms of the kinetic energy and our mg cosine theta. And we can look at the case where this is equal to or greater than 0. This is going to set a constraint on what the kinetic energy and mg cosine theta have to be as it moves around the circle. So now that we've got our normal force in terms of kinetic energy, and we've set that combination greater than 0 because that's the condition for it to be in contact with the track during the whole motion, we can now go back and look at an energy conservation approach because we just have to relate that kinetic energy to other quantities that we have known in the problem. So let's write our usual energy conservation grid here. We're going to look at the initial and final kinetic energy and potential energy of our roller coaster. And the initial position being the point where we release it from rest at the top of this initial slope. And of course it's at rest we've learned that the initial kinetic energy is equal to 0. And of course the final kinetic energy is the one that we're actually interested in this problem here. The initial potential energy is just that mg times our initial height, which we set out earlier. And now we have to figure out what is the potential energy at any arbitrary angle along this loop. Well, you can tell that if we look at this diagram, if we set the bottom here to be our 0 point, which is what we've done implicitly by setting mgh to be the height of our initial drop-off point, the roller coaster is going to go up to a height of r and then to a height of 2r as it goes around the circle. And so whatever expression we have is going to be some multiple of r times some function that involves trigonometric functions. And if we think about it a little bit, you will see very quickly that this is going to give us mg times r times 1 minus cosine theta. Now, let's double check that. When theta is equal to 0, cosine of theta is 1. 1 minus 1 is 0, and so that's exactly where we are when we start at the bottom of the circle. If we're looking at the top, cosine of theta now is cosine of 180 degrees, or cosine of pi. That's minus 1. So we've got 1 minus minus 1. That's 2 mg times 2r is the potential energy that we're looking for that case. All right, great. So now we can write down the total energy of the system, because that's the only potential energy we're concerned with. We've got mgh0 as our total energy at the beginning, and this is going to be equal to Ke plus mgr times 1 minus cosine theta. And again, it's equal to because we don't have any dissipative forces, and so we're not worried about losing any of the energy to those dissipative energy sources. So we can set those two equal to each other, and then of course that means we can solve for our kinetic energy as just mg times h naught minus r times 1 minus cosine theta. All right. Now it looks like a slightly complicated expression, but as we'll see, it will cancel out a lot of terms when we combine it with the rest of our expression. Now that we have an expression for our kinetic energy at any angle along this loop-to-loop, let's take a look at how we can substitute this back in and satisfy our condition for the normal force to be greater than 0, again at any angle around the loop-to-loop. So let's just go ahead and substitute this term in directly and see where we go. So we've got 2 over r, we've got mg times h naught minus r, 1 minus cosine theta, and then we've got our mg sine theta term as well. Sorry, that is an mg cosine theta. It's important to make sure we use the same trigonometric functions here. Right? And that's got to be greater than 0. Well, let's just carry through our terms here. We've got a 2mg times h naught over r. We've got the r's canceling here, so that's just minus 2mg. And then we've got a plus 2mg cosine theta, and then our other mg cosine theta, and all this is greater than 0. So immediately we can see that we can cancel out the weight terms here, and that's an interesting fact that tells us that the motion of this loop-to-loop is independent of the weight of the roller coaster. So now we can just solve for h naught by multiplying through by r over 2 and moving everything else to the other side. And when we do that, we get this is equal to r times 1 minus 3/2 times cosine theta. So this is the height that the roller coaster needs to be at in order to reach any angle theta around the roller coaster. But of course we're interested in making sure it makes it all the way around. It means it has to hit every angle. And the angle that's most important is making sure that it reaches up to the top of the roller coaster, and that's the case where theta is equal to 180 degrees, or pi radians. And that's equal to -1, so we have to have the case of h naught just equal to, but greater than, h naught greater than 1 minus 3 halves, or 5 halves times the loop-de-loop radius. All right? And that's it. That's our answer. And so we can double check to make sure that that matches our predictions. We originally assumed that it had to be at least as high as the loop-de-loop itself, which is 2r. And of course, 5 halves r is half a radius greater than that. Why do we need that extra half radius? Well, we need to have a little bit more energy to take into account the kinetic motion of the roller coaster as it reaches around the top of the loop-de-loop. If we go to zero kinetic motion, zero speed, that means loop-de-loop would just stop, or the roller coaster would just stop, and of course its next step would be to fall straight down. So we need to have a little extra energy by raising that initial starting point at least half a radius higher in order to keep this roller coaster to go all the way around the loop. So now we've solved the minimum height that the roller coaster has to start from. We can go back and look and see what happens if we make a mistake on this. What if we actually start the roller coaster from our initial prediction that it had to be at least 2r? Where does the roller coaster end up in that case, and how can we compute its motion as it leaves the track? Now that's an important phrase there, leaving the track. Where does it leave the track? Of course, that is telling us that we want to calculate the point where the normal force goes to 0, because if it leaves the track, it's losing contact with the track, and there's no more normal force. So we can start with our expression that we solved in the last class for the normal force. It's mg times 2 h naught over r minus 2 plus 3 cosine theta. This is just grouping all of the terms that we had in the last expression. And now in this case, I'm going to assume that we use an h naught equal to 2r as our initial height, so we can then rewrite this in terms of mg. This is going to give us 4 minus 2, so this is going to be 2 plus 3 cosine theta. And again, we're looking for the case in which the normal force goes to 0. So if I set this term equal to 0, then what matters is the part in here, which gives us that cosine of theta has to equal to minus 2/3 for this to be true. And you can actually calculate what that angle is. That angle is about 132 degrees. And of course, it's got to be greater than 90 degrees, because this is the face where the cosine of the angle goes to a negative number. So where is this on our track? Well, we start here at 0. We're passing through 90 degrees. This is about 180 degrees. And so somewhere around here, all right, that's about 132 degrees, is where the car would leave the track and cause all sorts of damage and bad things. So let's actually figure out then what's the motion of the track of the car after it leaves that track. Well, at that point, when the car leaves the track, we can draw a very simple force diagram of the forces acting on it. And since it's no longer in contact with the track, we don't have the normal force. We've already neglected friction and drag forces. So we're left with just one force acting on the car, which is mg. So this is now a constant two-dimensional ballistic motion problem. And the only thing we really need to know then is what the initial position and the initial velocity of the car is to solve for its motion thereafter. So how do we solve for the initial position velocity? Well, let's start with the velocity because that's the more interesting one. We know that we've gotten a term for kinetic energy, which contains our speed, and that's equal to mg times our initial height, which in this case is 2r, and then minus the potential for the final height, which in this case is just going to equal to minus r minus 1 minus cosine of our angle theta, and I'm going to make sure we specify that this is the angle at which the cart leaves the track, so we'll call that theta r. All right, and we can combine out these terms. This is just going to give us a 2r minus r, so we'll have one mgr term. And then we've got a mg times plus r plus cosine theta. So that's going to give us plus mg r cosine theta r. Or all combined, we've got mg r times 1 plus cosine theta r, which turns out to be easy to solve because we had to solve for cosine theta r is equal to minus 2/3. So this tells us that the kinetic energy is 1/3 times mg times r. And this is equal to the speed, it's equal to the kinetic energy, so it's 1/2 mv squared of our object when it reaches that angle. And so it's very straightforward to then solve for the speed of the object. That's just going to be 2/3 times g times r square root, just using regular energy. Now that's the speed. What we really want to use to solve for ballistic motion is the initial velocity vector. And so we actually have to write down the components of this. Well, the magnitude we've already solved for, 2/3 gr. Now we have to figure out what the components of velocity are. And we can actually get that fairly straightforwardly by just looking at the direction of motion that this cart is going in when it's at that point in the track. And of course it's following a circular motion, so that velocity vector is tangent to the circle, and it's tangent at an angle of 130 degrees relative to the bottom axis here. And so you can think a little bit about what the sine or cosine of the angles are. I again like to think about this in terms of where do we go to extreme values. So if we're down at 0 degrees, this velocity vector is pointed entirely in the positive x hat direction. So that means it's going to depend on cosine theta. So we can just write down the x as cosine theta. And it turns out that the y is sine theta r. Right? That's our initial velocity at the point where it leaves the track. And this is a constant number because we already solved for theta r. And so all these values are constant. This really is an initial velocity for our problem. And of course we can also compute the initial radius. That just comes geometrically from the point where it is on our track. And so if I choose the center of our circle as our origin point, we actually already know what the y-coordinate is, because that's 1r times 1 minus cosine theta. And the x-coordinate is going to be varying between, say, positive r and negative r. And it's positive r when theta is equal to 90 degrees. So that's got to be a sine term. So this is just equal to r times sine theta, comma 1 minus cosine theta. And since this is our initial position, this is the angle at which it leaves the track. So we've got an initial velocity vector, an initial position vector. We've got an acceleration that's purely in the y direction. And this is simply a ballistic motion problem. So there's all sorts of ways that we can look at, for example, how far over does it land based on, primarily its x coordinate of velocity. How long does it take to fall down? Right? All of these things go back to our ballistic motion problems, and that's where we start to dive in back into our kinematics. So hopefully with this problem you can see there's lots of different ways that we can incorporate energy, forces, and kinematics to ask all sorts of things about the motion of this roller coaster ride. And of course we didn't talk too much about friction and drag force, but it's entirely possible to include those terms in because we know that the normal force, we can solve that for the angle at which it's going around the loop-de-loop. And so all we have to do is integrate the work done by that friction force times the path length along the loop-de-loop, which is just r times the angle in which it covers. That's hard to do analytically, but we can do it fairly simply with a computer expression. We've also shown that we can solve for the velocity, or speed, at any given point along this motion just using energy. And that means that we could also solve for the drag force. Again, easier to do in a computer than to do as an analytical expression. And that's why many of the simulations to predict how roller coaster rides go are based on computer simulations. The physics themselves is actually not that difficult, maybe difficult than you're doing in this class, but it's just much easier to do with a computer simulation. In any case, when we get rid of those drag and friction terms, we end up with a very clear expression for what the motion is going to be throughout the loop-de-loop, whether or not it stays on the track or not.